Okay, Rose, here's the third video in a series on sum and difference identities. And this third problem is a little unlike the first two, because in this problem, I'm going to give you information about sine of an angle and sine of another angle, and you're going to find the sine of a minus b, or actually in this problem, we're using Greek letters. It's alpha minus beta. So I'm going to read the problem to you. Again, pause, rewind, whatever you need to do. So problem number 3 on my page says, given that the sine of alpha is root 2 over 5, and the sine of beta equals 1/2, where alpha and beta are in quadrant 1, find the following. Part A says, find the sine of alpha minus beta. All right, here's the deal, Rose. If you want to find the sine of alpha minus beta, write out the identity, okay? And again, these are on page 287 of your textbook, but I'll read it aloud. The sine of alpha minus beta, I have a jingle I use. It goes sine, cosine, cosine, sine, keep the sign the same. Sine, cosine, cosine, sine, keep the sign the same. So it would be sine of alpha minus beta would be sine alpha cosine beta, right, minus the cosine of alpha times the sine of beta. And again, there's no distributive property for angles. That's why it's such a glunky formula. But hey, don't blame me. I didn't make it up. You understand? All right, now you were given that the sine of alpha is root 2 over 5. So in my formula, underneath sine of alpha, I can put root 2, I can put root 2 over 5. And I was given the sine of beta equals 1/2. So underneath, in that little formula, underneath sine of beta, I'm just going to replace that with 1/2. Right, the problem is, my formula, I need to know the cosine of beta and the cosine of alpha. I don't know either of those. I wasn't given that. But guess what? If you're given the sine, you can find the cosine by using reference triangles. Whew, how about that? So the sine of alpha is root 2 over 5. So I'm going to draw a triangle, a first quadrant reference triangle. And sine of alpha is root 2 over 5. That's the y-coordinate over the hypotenuse. And if I do the Pythagorean theorem, if I square the hypotenuse and square the y value and subtract them, I get 25 minus 2. I get 23. So the x-coordinate would be root 23. That's for alpha, which in my triangle, x over r would be root 23 over 5. So one of the problems with this is the numbers, man, they get ugly. So in my big formula, cosine of alpha is root 23 over 5. And then I also have to find cosine of beta. And to do this, I'm going to draw another reference triangle in the first quadrant. And in the setup of the problem, I was given sine of beta is 1/2. And that might be one you can do in your head, because if the sine is 1/2, the cosine has to be root 3 over 2. But if you draw the reference triangle, the opposite is 1, the hypotenuse is 2, the adjacent's root 3 by the Pythagorean theorem. So yeah, the cosine of beta is root 3 over 2. So, in my problem here for sine of alpha minus beta, now what I have is root 2 over 5 times root 3 over 2 minus root 23 over 5 times 1/2. And all I have to do is just simplify that a little bit. And if I multiply things out, again, I have a common denominator of 10 because I have 2 and 5 on the bottom. And in the first two fractions, the numerator is root 2 and root 3. That's root 6. And in the second set, I have root 23 and 1. That's root 23. And that's my answer. And it's a hideous answer, but the final answer to this is root 6 minus root 23, the whole thing over 10. Okay, hope that helped. Hope you're able to follow that. If you can't, boy, I don't blame you. These problems are tough. I'm going to hit the stop here and maybe make